Yep.
So
So
feel free
yeah,
to
we'll go ahead
go.
and we'll turn it over to you, and we'll monitor questions and things like that. But let us know if you need anything.
All right, sounds good. Yeah, thanks for having me on. I come from a dev background primarily. Went into AppSec, so I've done a lot of AppSec work. Ironically, in the last couple of years, it's been all cloud stuff. So my talk tonight is mostly, it's a little less AppSec. It's kind of a vision that I had of, well, let's assume that your serverless environment is compromised. Like we would never write insecure code, would we? And put a vulnerable function into a cloud environment. And the approach I took was let's assume breach and look at cloud native controls, what exists inside of all three of the big three clouds for helping security, incident response, networking folks get some visibility into these cloud services that are running these little micro functions that are starting to take over and power a lot of the application world. So hopefully most of you are familiar with these up to this point. AWS Lambda obviously is the most long-lived here. Azure functions and GCP functions are a little less documented from the security side. So what I intended to do with this research was double check that all the things I had read in Lambda were true, which they are, and then figure out the equivalent approach that I would take in the other two clouds. So I'll bounce around a little bit. I've got some demos and stuff that I recorded for a presentation I gave back when we could actually travel at RSA last February. And it's actually exciting to revisit this material and present it again because it's been a while. So what are the goals here? One, it's hard to reverse engineer an execution environment when you cannot actually SSH into it. So you kind of have to throw some malware into each environment and get a reverse shell. So we'll talk about how to do that. I made it pretty easy, along with some help from a colleague, Brandon Evans, to stand up command and control between all three environments. We'll poke around a little bit. We'll see where some secrets might be. The fun part is actually exfiltrating the authentication tokens from each provider's environment that they bootstrap with for you. And then we'll look at using those, pivoting into other parts of the cloud, and then take a blue team approach in the back half. What can we use for detection via logging and maybe locking down the environment to prevent some data exfiltration? So this was a fun little 2-month project, just poking around in all of the different functions. And I'll give you, a little 45-minute tour through the highlights. Overall, as you're looking at the environment itself, I have questions from a red and a blue team perspective. If you're trying to compromise this thing and break out, or potentially compromise the container, what user are we executing as? What OS is the function running in? What default directory am I sitting in? Where is the source code actually at inside of this container? What are in the environment variables? What service account am I running under? And then can I write to any of the directories inside of said function environment? So that is the project that we started with. And just like all things that I do at Puma, we pretty much name ours after cute little animals. So the open source repo that all of this research is sitting in is called Serverless Prey, and it's got code inside of it, some Terraform for Azure, because the serverless framework that we used for AWS and GCP wouldn't work. So it's a combination of serverless and Terraform to launch a Go function into Google, a C# function into Azure, and a Node.js function into AWS. So we wrote 3 different functions, picking kind of the, a native-ish language for each one just to entertain ourselves. All of that is out on the GitHub repo, out on our site. So feel free to poke around in there. Each directory, Cheetah, Cougar, and Panther, the names of the functions, has a doc that's got all the notes, all the commands, and everything that I'll walk you through here in the affiliated slide deck here. So step 1, deploy the functions. Step 2, invoke each one. They both take a host IP, which is your attacker machine, and a port that you spun up netcat on. And all you have to do is invoke the function, and the function environment will give you a reverse shell back so you can actually run some commands and inspect the environment that your function is running in. So that's that simple. That's how you can get a shell into a function and poke around a little bit. The first thing we looked at was, well, what's networking like here? Do we have access to the internet? Clearly we do because, well, the reverse shell worked. Are there any other controls that stop us from talking to malware servers or to AWS or GCP or Azure APIs or anything like that? Turns out no. Your function is deployed into a shared VPC inside of their serverless environment with full egress to the outside world. So you can do whatever you want out of the box. So it's important to realize as a cloud security or even AppSec or DevSecOps practitioner, whatever your job title is, you're responsible for locking this down if you need it to be. Next up, let's inspect the OS a little bit. Where are we? Node runs on Amazon Linux 2, no surprise there. .NET Core, so I launched the Linux version of .NET Core, so I don't really deal with the Windows stuff much anymore. You can run it on Windows if you want to, but if you pick the Linux side, you're in a Debian Linux instance, running the Go function, you're on a Ubuntu 1804, at least as of the last time I tested this, which is within the last month or two. Default directory, var task in AWS, you're on the root of the file system in Azure, GCP, or at SRV files. So that's where you will be sitting if you ever get a reverse shell into one of these. What user are you running as? AWS, it turns out, is the only one that thought running as the root user in the container was a bad idea. Both of the other ones, you're running as root in the container, which even if it is isolated, by gvisor or Firecracker or whatever their micro VM technology is, it still isn't a good look. So AWS is the only one that took the time to generate a random user and run the function as somebody else. So that's the overall snapshot of the execution environment. Where's the source code? Because that's ultimately what you want. Normally you're wanting to exfiltrate source code, read it, see if there's vulnerabilities, see what services it's communicating with. Can I grab data from S3 or an Azure blob or a GCP bucket, whatever it is. So if you want the code, you go to var task in AWS, which is the default directory. In Azure, there's a little bit of IIS showing there. Home site www root is where the Azure functions are deployed to. And GCP is also in the default directory, your SRV files directory. So a couple basic examples. Once you're in there, this is me in GCP, works for all of them. So we'll do an ls, what's in SRV files? And then you start to poke around, right? Oh, cool, there's the Go function, we could read that. Oh, interesting, there's a YAML file. There would maybe potentially be secrets in the YAML config file, which you can easily cat out and get access to. So you just start typing around like anything else inside of the function execution environment. The big difference here is eventually it's going to time out on you. So there's a little bit of a limitation on how long you can play around here before you get disconnected. Brandon Evans, the gentleman that I worked with on this, got annoyed by that. So he wrote up a shell script that actually, if your C2 channel gets disconnected, it auto reconnects back to the function again by just re-invoking it and standing up the C2 again. So if you use our script, there's a pray.sh script in there, you may not even notice that you're getting disconnected, which is kind of fun. Environment variables. Now I'll show you some other examples of this later. Basic LFI in any of these functions can give you the ability to just cat proc self environment and see the environment variables. AWS has some cool stuff in theirs. I'll show you that in a minute. Azure has even more cool stuff than AWS in theirs. GCP has hardly anything useful in their environment variables. So I'm showing you the Azure ones, which has a lot of encryption keys. There is a connection string to the Azure storage blob or the Azure storage account that it's actually downloading the function deployment package from. So you can actually pivot from the function into the storage account just based on the environment variables. It's got an app site's instrumentation key, which is all telemetry. So all your function metrics, how long did I run for, what log files went in there, all of those fun things you can get to using the app insights key. There's an encryption key for kind of decrypting the incoming API keys that are auto-generated as well, which is fun. And then you've got the MSI, their managed service identity, secrets, and endpoint also live in the Azure Functions environment variables. We'll take a look at what that looks like here in a minute. So let's go to demo number one. This is the GCP side. So you're staring at an EC2 instance that I'm just using for the Netcat listener on a public IP. Let me kick this thing off here. We'll kind of watch how you can do this once you launch this project out the door. In burp, that's invoking the function to the public IP on port 1042, and we've got a Netcat listener. So that's how simple it is. We run ID. Yep, Google's definitely running as the root user inside of the container. We'll go ahead and see what OS we're running on. Matches up with the slides. Where are we? What's in the directory? So you'll see those same sort of deployment files from the actual serverless deployment package pop in here, and then lo and behold, we'll dump this YAML file out. So once you get them deployed, that's how simple it is to start poking around in the environment and investigating things. All right, so let's pop into the next topic here. Rather than hard coding credentials, which is kind of a no-no, right? We don't really want to deploy creds into the environment in order to access backend resources in the 3 clouds. So instead of doing that, they all offer an execution role that you can attach to the function, or a service account, if you want to think of it that way. Depends which cloud you're in. So AWS Lambda calls it the execution role. Azure Functions call it the managed identity, which is a virtual Active Directory user that you actually will never see in real life. They create it. It's kind of hidden from you in Azure AD, and then you just see this random ID that you can then assign permissions to for talking to storage, talking to Key Vault, and that sort of stuff. GCP's service account is what theirs run as, and theirs is almost the opposite of Azure. Theirs is just right in your face. Here's the default service account that we're auto-generating for you, and we're giving it full permissions to the entire project that this function is running inside, which is a little egregious from a least privilege perspective. Now, GCP's org structure, they very strongly push you towards using projects to isolate workloads. So they don't want you to use one project and think of that as comparable to an entire AWS account. But some folks do that. And this function, when it comes to life out of the box, has full read and full write permissions to the entire resource group inside of that project. You've got to do something to turn that off. So that's a gotcha. Something I was frankly shocked when the first time I spun a function up and realized that I could exfiltrate everything in the project from the function, which is pretty cool from a red team perspective. The other service accounts are very least privileged. Okay, so we've got a service account, functions alive. How are the creds bootstrapped into the environment? Where do they live at? Now, AWS Lambda, I had known where these live just from reading the Rhino Security and seeing Scott Piper tweet all about Lambda. And so we knew they were in the environment variables. They're still there to this day, to my knowledge. So very simple to find. Azure's and GCP's require a little more research. GCP's, they actually attach the instance metadata service that you would see on an instance, on a GCE compute instance, to the function. So that's pretty well documented and easy to find. Azure's is not in the environment variables, and it's also not using an instance metadata service like their Azure VMs do. Instead, it's actually a couple of pivots to get to it. So I showed you the managed identity environment variable, and there is an endpoint in the environment variables to this local host URI and port. And then there's a secret also in the environment variables. Once you have those, you then need to make a GET request with the secret in the secret header to the MSI endpoint value, tell it which version of the MSI endpoint you want to pick, and also you have to give it which resource or which API are you wanting to talk to with the token that's returned. So there's a lot of work that goes in to grabbing or exfiltrating a token from their environment. Everything in Azure is using JWTs, which I did not know until I started poking around at this stuff. So all of their API access is JWT driven. The resource that I had to put in on that MSI request is the audience that ends up in the JSON web token. So this token that you just stole is only good for talking to the storage service. If you need to talk to the key vault, you've actually got to run your payload through again and grab another JWT scoped to the key vault service and so on and so forth. So in my opinion, Azure actually makes it the most difficult to exfiltrate all of the things from, because you got to make a lot of different requests to that functions, to the function to get access to everything. So it's kind of a cool pattern that's inside of there. Flipping gears to Google. Google actually has a lot of different versions of their metadata service. Version 1 requires the custom header that you've got to set, metadata flavor to Google in order to talk to the metadata service to prevent SSRF attacks from easily extracting tokens from their environment. As it turns out, their beta metadata services, V1, Beta 1, there's also a .1 version that's still available on compute instances. Even though they're deprecated, they're still active. Their function environment does not have .1 active, but it does have V1, Beta 1 active out of the box. And you have to do something to actually turn it off. So if you don't want this very basic SSRF vulnerable endpoint to be available, we're just curling metadata Google internal / yada, yada, yada service accounts default token to get the OAuth bearer token for the environment back. In every single function, you have to set the disable legacy metadata server endpoints environment variable to true to block requests to the vulnerable implementation. So that was kind of fun to run into as we were poking around with this stuff. Okay, and then we have tokens. What do you do with them? How do you use these things to actually do some damage in the account? Now, AWS, again, is the easiest here. Their values are in environment variables. All you do is set 3 environment variables in your shell and you're talking. Azure's and GCP's are a little bit harder. You actually have to craft REST API requests, which anyone that's worked in dev and AppSec long enough, you're probably cool with this, but there's a lot of red teamers out there that are not comfortable writing raw HTTP requests. And that's kind of what you have to do in their ecosystem because they're returning OAuth bearer tokens or JWTs to you. So on the AWS side, this is how simple it is. Set 3 environment variables to what you've dumped from the environment variables in the function, and boom, you're stealing the image of the Panther right out of the S3 bucket from your laptop at home instead of from inside the function. So that's how simple it is to use. As we look at some of the other options here, I'll show you the demo of the Azure side here in a sec. As a blue teamer, you're immediately concerned, right? How long do these credentials live for? If you remember, the signed JWT in Azure, that's not changing. Unless you go in and just revoke the permissions from that managed service AD account, it's going to live for however long you signed it for. GCP functions is an OAuth bearer token, same drill. So those were really easy to see. Google's 30 minutes, that's it. So if you're an attacker, you better do your damage really quickly before that thing expires. Azure and AWS, way longer. So the JWT in Azure expires in 8 hours. Does that seem excessive for a function that runs for 300 milliseconds? Seems odd to me that it lives that long. That's just the way the platform is drawn up. We cannot change or modify that. It's not configurable. So that's just, you have to live with it. AWS is even worse, and of course it's not documented whatsoever. Either their creds, their access keys that you dumped, live for roughly 12 hours. And the only way that we were able to actually find that out is just by issuing a request, write up a little job that runs every hour and say, hey, are these creds still valid or not? And eventually after 12 hours, they expired. So you've got some serious time on your hands as an attacker when you steal the creds from a function that runs for 300 to 500 milliseconds in Azure and AWS to use them and exfiltrate from the environment. Next, we looked at persistence. So these functions are supposed to run for 300 milliseconds and go away, right, when they're done. There shouldn't be an opportunity for persistence here. As it turns out, that's not exactly how they work. So there's a concept of a warm environment and a cold environment. The cold environment is fresh. There's nothing in it except for the function, and then it lives for a while. So even though your function only ran for 300 milliseconds, when you do something like write a test malware sample, we threw the iCar virus down into the temp directory, for example, let the function go away, and then we execute it again 2 minutes later and the malware was still there. And it's because that function execution environment lives for a bit to avoid the overhead of firing up a new cold environment every single invocation. So there is some persistence here. The processes running do seem to shut off and go away, but your malware could be re-invoked on every single execution without having to rewrite the file into the containerized environment. So the question again, how long do these warm environments stick around for if you're not actually invoking the function? This was a little bit of a moving target. So you got different numbers every time we tested it. On average, AWS Lambdas, 11-ish minutes is how long that thing lives for. Azure functions will stick around for about 6 minutes with your malware in there before it disappears. GCP functions, again, the most recycled, about every 3 minutes. Those went away. So that is the snapshot of credentials and persistence inside of the execution environment. Let's poke around with Azure here. This is actually pretty fun. So we'll do the same thing. We're going to establish a reverse shell into, this time, the Azure function. So we'll see this pop up our Netcat listener here. And what we're going to do is we actually need to grab the JWT from that MSI endpoint. So we invoke our MSI endpoint with the secret. Now we've got the JSON web token scoped to storage.azure.com. And we'll just copy that out of the function over to the attacker's machine. And I've got all these requests preloaded up just with a $ bearer token in there, just to make it easy to just paste in the token and rock and roll. So you can see right now I'm asking what storage accounts do we have. You can see the audience scoped as it runs its way through the burp side. And we can see, yes, there is a storage account there. Let's look at the containers inside of it. So we've got an images container. And of course, I've got my pretty picture of our cougar friend inside of there. Inside of the container, now let's list the blob objects inside of the images container. Play the same game. Yes, there's an image. And then on the third request, we'll actually pull the image out of the bucket, or the blob. Sorry, I call them all buckets, even though I know Azure has different terminology. All right, so now we can see the raw image contents. And you can play the same game With the key vault, you just have to go back in and request a different token scope to the vault service instead. So that's how simple it is to use those tokens in Azure, as long as you know where they are. That was the hardest part, was just finding them. Coincidentally, there's not a lot of documentation on where that thing lives. So there was an obscure posting about the managed identity service that I found. And ultimately, I ended up in the Azure Functions web job GitHub repo. So thanks, Ken, for having all the folks make that public. And all I did was I went into the managed identity class inside of there and actually saw how they were grabbing their credentials from the functions environment. And that kind of tipped me off on where to go locate those things. So open source is awesome for that stuff, right? All right, let's switch gears. Let's go blue team a little bit. We'll try to figure out, did we leave a trail behind us as we did all this stuff? And there are auditing tools in all three clouds. You've got to turn them on in order to actually see what just happened. So CloudTrail is probably the most well-known AWS audit service. As long as you've got CloudTrail turned on and you're capturing data events from S3, you would see me taking those tokens and swiping that picture from the bucket from a rogue IP address that clearly is not an internal Amazon function IP. On the Azure side, this was a little bit of a headache. Azure Monitor, I would say, is probably the least mature out of the three of these because you can't turn it on globally. CloudTrail and IAM audit logs, you go to that service and say, capture all the things and you're done. In Azure, you have to go to every individual resource. So think your Azure storage account, you have to turn on diagnostics. Azure Key Vault, you have to go turn on diagnostics. And if you've got 38 key vaults, you have to turn on 38 different key vault diagnostics in order to get the audit logs that you want detecting these exfiltration attacks. So infrastructure as code is really important here, right? Make sure you've got a module that automatically does that for you. Otherwise, you're going to miss the glorious information that you're seeing on this slide. So this is me querying Key Vault info, saying, all right, the resource provider is Microsoft.KeyVault. It's a little Custo query that you can use to query their diagnostic log tables. And we're looking for the resource name, which in this case, the Key Vault key I was pulling out was the Cougar database password. And you're looking at some interesting caller IP addresses here. So let me zoom in on this a little bit so it's easier to see. So this is really what you're looking for almost from an IR perspective. So 20.189, that's an Azure IP. So that's normal activity for a function running in their environment. However, then you can see me, the random IP, doing the same thing with the same username, the same managed identity ID. So suddenly you're freaking out, right? Because that shouldn't be possible. It allows it to happen because it doesn't really have any restrictions on where it can be invoked from out of the box. You've got to do something to make that happen. So let's look at some of these access controls. Where are we sitting here? We got about 15 minutes left. Should be good to go on getting through the last blue team discussion side of things here. In order to gain access to any of this stuff, you've got to yank the function out of the quote managed VPC that they default into, the network that they're running in, and you have to bring it onto your side of the responsibility model. So in Lambda, you integrate it with the VPC service. In Azure, you have to upgrade to a premium function plan. So you've got to pay a little bit more money. What this actually does under the hood is it turns your function from an on-demand consumption based, where you only get charged for 10 milliseconds of execution time. It puts you in a full-time running function environment. So all of those persistence things I talked about, those are out the door because now the function is just alive It's basically like turning it into a full-time server. But when you do that, you get VNet integration. So you can take that function, put it in a VNet, and then you can start setting up egress filters and VPC flow logs and a lot of the stuff we'll go through. On the GCP side, this is challenging to set up, but mostly it's just because I didn't understand how GCP wanted me to do it. GCP, like I said, is very project isolated oriented. So in order to set this up, you need to create a host project that has a shared VPC in it. You need to share that VPC with your function project, and then you need to have your function turn on the serverless VPC access feature and launch all of its traffic, ingress and egress, through the shared VPC. So it takes a little bit of work to get it set up, but you've got some really tight centralized controls there on watching what your functions are doing if you go through the headache of getting it set up. When you do that, where we're going to land here is your function's probably broken because you've gone from a network that has an internet gateway and public IPs to a network that you're in charge of that doesn't have any of that stuff in it. So you've got to go through your progression of setting up a NAT gateway inside of the VPC for egress and responses. And then you've got to go in and turn on some of the other hardening techniques we'll talk about to lock down some of the resource traffic from an exfiltration perspective. So we did this for the Lambda function in this scenario. This is the serverless framework. So there's a serverless.yaml file that's in the repo that I pointed you to earlier. And if you flip an environment variable when you build it, it'll put you in a custom VPC in private subnets with the NAT gateway, and it'll set up a security group rule that allows you to set up some egress filters. Security groups is the resource in AWS you want. Network security group is how you would do it in the Azure VNet, and then GCPs are just called firewall rules. So they're actually very simple to work with and set up. And then you can start blocking the outbound C2 connection on port 1042. So we've kind of got that green path highlighted at this point. So we're forcing our egress traffic to go over port 443, for example. Here's the code that you'll see fly in here when you do that. So when we're even locking this down, instead of all zeros on the CIDR block, we've got maybe the trusted corporate network. Maybe that's an upstream proxy that's going to capture and inspect and do all the next gen firewall things to our function traffic. Whatever it is that you need to set up, that's where your traffic has to route through. From a network forensics perspective, about the best you can do here is setting up flow logs. And in some cases, I don't know, and maybe somebody out there knows, I don't know if you can do traffic mirroring from a function network interface. I haven't seen it done. Maybe it's possible, but flow logs are kind of aggregate net flow data that give you some indication of the source and destination ports and IP addresses that the function's talking to. In the Azure world, network security group flow logs, same thing in GCP. So you can turn all those on. It's very simple. Get the log data into the centralized logging service so we can query it and actually detect that C2 channel getting blocked on port 1042. So I'll show you what that looks like here in a minute. The query itself, now this is against a CloudWatch log group using CloudWatch log insights. But you could also use the Kusto query I showed you over in Azure to query their log source. And in GCP, it's a little bit different of a syntax, but the same drill. You can see in the output, I'll zoom in a little bit on this. We're now getting the traffic flow to port 1042, the demo that I showed you being registered in the function's flow logs, which is way more visibility than we started with. Now we know that C2 is happening. The next question is there a way to block the credentials that we stole from the function from actually being used outside the environment? Can you do that? And as it turns out, a number of services, not all of them, but a number of services, the common ones like Secrets Manager, the buckets, the storage services, the vaults, the key management service, they all support internal routes from the VPC without having to traverse over the internet. So in AWS, you're looking at VPC endpoints. In Azure Functions, you're looking at Azure private endpoints. And in GCP, it's a little bit different. You set your VPC up to route DNS. All Google APIs will go to the restricted Google APIs. So those are internal routes to the GCP APIs. And once you do that, you can turn on a control called VPC service controls, which sets a perimeter around one too many projects. So if you set that around the project that has the storage bucket and our secrets in there, the data inside of that project cannot leave the perimeter. And by default, VPC service controls keeps it all inside of the GCP virtual network. It can't leave. Unfortunately, that blocks you out as an administrator from even from the web console. You cannot browse to a storage bucket inside of that perimeter unless you poke a hole in it and say, here's some administrative IPs that are allowed to do this thing, whatever the action you're trying to do is. But all three of those will force your function to talk internally on the network to the APIs and block the outside world from stealing the images or the secrets, whatever it is that you're worried about being exfiltrated. So nice exfiltration controls there. The example on the slide, this is us setting up the endpoint for AWS. So we're standing it up for S3 and then applying a bucket policy. This is how you would do it on the AWS side per resource that ultimately says, look, this principal, which is the role the function is running under, cannot get images from this bucket unless it comes from the VPC that we expect it to be in. When I steal the keys and run them from my laptop, I'm going to get access denied because I'm not coming from a trusted location. So it's a way to lock that down from that perspective. And then you'll also, when I get that access denied externally, you're going to see CloudTrail pop up and say, weird, this user ID suddenly jumped over to this IP and I rejected the request. So you'll have that audit trail. Okay, so let's do the last demo. Then I'll give some shout outs to some folks that helped out and or motivated me to work on this a little bit, figure out how all this stuff works. Last setup, this is the AWS side. So same deal. We've got the Netcat listener running. Now with egress in place, so we're filtering all traffic on port 443. Notice it's dead. We're not getting our command and control on port 1042 because the egress security group rule is blocking that. So that's a win. That activity is also conveniently, because we've got it in our own VPC with flow logs on, we are seeing that reject in the flow log traffic at this point. So it's a nice little network forensics add-on is, yeah, we're actually monitoring what our functions are up to at this point, which is much appreciated by the InfoSec team. So I ran a logs query. Here's me grabbing the results back out. And this should show us the reject coming from wherever I happen to be in the world when I ran this demo. So there it is. There's the function IP. There's the external IP that I ran it from. Port 1042 is what I tried to get C2 on and rejected. We shut it down. So let's try again. Let's do what any good attacker would do, which is let's just assume that port 443 is allowed outbound because it always is. We'll flip over to port 443 and get command and control and dump our creds that way. And of course it works. So now we're grepping the environment variables for AWS for the access and secret key and the session token. We need that too. So there's the 3 values that we need. So we'll quickly just set our 3 environment variables so we can authenticate to the AWS account as the function. And one more to go here. And let's try to dump that S3 object. So here we go, the big moment, the data exfiltration, access denied, which is what we expect because we've got the bucket policy in place, establishing that trusted perimeter for that particular user ID. So we can't get to it. Now I've got all the CloudTrail logs pumping into an Athena table, and we're going to search for requests from that function identity. So we'll see what shows up in the CloudTrail logs. Hopefully it shows our attacker trying to get in there and exfiltrate data. And then we've got some incident response scenarios, obviously, that we would probably kick off, hopefully. So filtering down to access denied, and there we go. There's the S3 request to list objects from whatever IP address I was at when I ran this demo. So overall, that concludes the walkthrough of all of the various security controls that we discovered missing and or available across all 3 functions, platforms, and the big 3 clouds. Primary motivation here, Gal Bashan actually has an awesome write-up from a few years back called Lambda Internals. And when I read it, I thought to myself, that is so cool. AWS focused, that was part of the motivation for exploring how you could do the same sort of thing in GCP and Azure. Shout out to Brandon Evans, a buddy of mine who helped me get used to writing serverless framework deployment files and getting these functions set up. He's been an awesome contributor to the project. For those interested in more of the AppSec side of serverless security, there is a flavor of kind of an OWASP top 10 project out there for serverless. It was mostly contributed by PureSec and Pertigo, 2 big serverless security companies that do quite a bit of research in the area. So some other resources for following up, learning more, etc. With that ties off the walk through defending your serverless infrastructure. Thank you all for attending and hanging out. I'll pass it back to Seth and Ken for some conversation or whatever y'all have going on.